Good morning, students. Today we are going to continue the last session. So, in the last session, we have seen what are the different types of assemblers which are there in the market, and what are the steps which are going to be followed by the assembler in order to execute our program. So, in the last session, we have seen the what exactly the editor block, what exactly the assembler block, what exactly the linker block, what exactly the locator block. Okay, so let us review that one once again. So here what we do is yeah, I'm going back to the slide. So here we have seen the editor window. Editor window means where we are typing our program and saving our program, uh, and where we can edit the program. So that is called as an editor window. And that particular editor window, soon after you type your program, you are supposed to save your program with the .asm extension. Okay, now so here these are the steps now. So up to the debugger is the different one. So from the editor to the locator, this entire thing is going to be processed by the assembler. Of course, the debugger is also there, but it is not in the sequential. So if you want to see that one in the diagrammatical manner, this is what we are having. Okay. So the editor window means where we are typing our program and saving our program with the .asm extension. We are typing the program, we are modifying the program, and we are adding some extra information to the program. And all those things are going to be done in this particular window, and we are saving that file, that program with the extension of .asm. Here I am assuming that my file is a name of my program. My file is a name of my program. My file is a name of my program. Okay, now. So my file is the name of my program, and I am saving this file with the .asm extension, okay now. So here in the editor window we type the program and we are saving the program with the .asm extension, and here the .asm extension file is given as an input to the assembler. It is given as an input to the assembler. Okay now, so this assembler is accepting the input in the form of the .asm extension, and it is converting this file. It is creating two different files with the two different extension for your file. Okay, means my file is a file name, my program name, and this program name is going to be two more files with the two different extensions. One is a .lst extension, another one is a .obj extension. So another one is a .obj extension. So this assembler is creating the two different types of files with the two different extensions. One is a .lst extension and another one is a .obj extension. Okay now. So .lst extension, in the last class we have seen that the .lst extension file is going to be includes all the information. Means here you are entering only the in the editor block you are entering only the mnemonics, whatever the instructions which are there in your program. You are simply entering that instruction and saving that file with the .asm. Now, so in the .lst file, the assembler is going to be assigns the addresses. Means this one is going to be shows the what is the virtual address which is going to be there to each and every instruction, and also it is going to be list out the opcode for your program. Here you are entering the mnemonic, not in the opcode format. Mnemonic is nothing but the instruction format, but in the data list file you are going to have the opcode to each and every instruction, as well as you are having some relative address. Okay now, so some address is going to be assigned by the assembler. Exact address is there in the locator case. So up to that point it is going to be shows the address, opcode and the mnemonic. Okay, actually you are saving the file with what, you are typing your program with instructions. You are not assigning the addresses, you are not assigning the opcodes, but this one is converting your instructions into the opcode format, equivalent opcode format, as well as it is going to be list out the addresses. Okay now. So this is the data list file. Now .obj contains the what is that, opcode as well as the addresses. .obj contains the opcode as well as the addresses, and it is an object file which is there in the binary format. You as a user or the developer, you can't predict that one. It is specific to the microprocessor. It is specific to the microprocessor. As a developer or the programmer, as a developer or the user, you can't realize this particular file. Okay, which is there in the binary format, but which includes the opcode format as well as the addresses. Okay now. So as I said, the .lst file is more useful. .lst file is more useful for the developer. So means once you type out the program and you are trying to execute the program, here are somewhere you are coming across the errors in the program. And if you want to check it out where exactly the error is occurred, So whatever the developer, whoever the developer is there, that particular developer is going to be visits the data list file to check out the error occurrence. Means the assembler which is creating the data list file, it is going to be list out the errors also. If at all any error is there in your program, that error is also going to be listed out in the data list file. Okay now. So as I said in the last class that the object file. So we are having the assembler creating the data list as well as object now, and this linker is going to be links the different types of object files. Okay now, different types of object file. So one object file is our own program, and another object file means this program may depends on the some other factors. That factors information is there in the .obj file, and that .obj is also going to be included. That our .obj is going to be included means whatever the necessary .obj files which are required to execute your program, those .obj files are also going to be accepted by the linker, and the linker is the one which is linking all the .obj files. Linker is the one which is linking all the .obj files. Okay now. So because in the last class I told you that when the developer wants to develop one application for a particular institution or the organization, obviously that institution or the organization information is going to be divided into the block format. For each block they are going to be develop the individual programs, and each program, for example, for the principal they are writing one program, and that is called as a module, one module. And for the students they are writing one separate program, that is called as a student module. And for the staff they are creating the they are writing a separate program, that is called as a staff module. Like that means the application is going to be divided. Actual application is for the college, but that application is divided into the module format, and they are developing the programs individually, and they are integrating all the modules together to generate one application which is nothing but the college application. So that is going to be done by the linker. Linker is going to be what links all the .obj files which are needed in that particular application. Okay, and all those .obj files are going to be linked by the linker. And this linker, after linking all the .obj files, it is creating one more file with a different extension which is nothing but the exe. Okay now, with a different extension which is nothing but the exe. Okay, so this linker is integrating all the .obj files and creating the .exe file. It is creating the .exe file, and this see, this linker is linking all the .obj files now. It is linking all the .obj files, as well as it is assigning the relative addresses to the instructions which are there in this particular program. Okay, so it is assigning the relative addresses, not the physical addresses. Relative addresses are nothing but the, I can use another word called as a virtual address. Okay, so it is not the exact address, it is giving the a relative address. Okay, so relative address means we are expecting that that address is there in the memory, but that may not be there in the memory, because during the execution of the program actual address is going to be assigned. Till that time we are having the virtual addresses as well as the relative addresses. Okay, so this linker is assigning the relative addresses if at all you are having some jump instructions, and creating the .exe file, and this .exe file is given as an input to the locator block. Locator block is a one. Locator block is nothing but it is going to be maps your program into the memory. Let us suppose this is my memory. Sorry. So assume that this is my memory. Okay, this is my memory, and whenever you are using the locator now, so till the locator, before the locator, the linker is assigning some addresses now. Those are called as a relative addresses. That addresses may or may not be existed inside the memory. That addresses may or may not be existed inside the memory. I'm just taking this one as a memory block. That address may or may not be there in the, that address may or may not be there in the memory. Okay now, so that is done by the linker. Okay, if at all, if at all, means linker is assigning the relative addresses, means virtual addresses. It is expecting that that address is there in the memory, but that may not be there in the memory. So here the locator is the one which is going to be locates the memory, which is going to be assigns the physical addresses, actual addresses. We used to call that one as a absolute address. Means this entire file, the my file dot bin, this entire my file. Wait a minute. My file dot bin is going to be stored inside this particular memory. It is going to be stored inside this particular memory. Okay, so it is going to be this entire file, whatever the file which is there at the output of the locator, which is converting the executable file. Executable file is there in the hexadecimal format. What is the executable file means? Don't get confused. Executable file is there in the hexadecimal format, but the hexadecimal format information is not going to be executed by the system, as we know that one. It should be there in the binary format. So executable file is converted into the binary format, and that binary converted binary format is exactly loaded into the memory. So means exact physical addresses. Physical addresses they means which are there in the memory. So till this one we are having the relative addresses means which may or may not be there in the memory, but in the locator case it is going to be assessed the exact addresses to your instruction. Exact addresses to your instructions as well as the jump instructions, whatever the jump instructions you are having. So this locator is converting the exe file into the binary file, and it is storing that information in your program into the memory. Okay. So this is what the procedure which is going to be done by the what is that MASM assembler, macro assembler. We are studying about the macro assembler. Okay. So means the macro assembler is having one editor block where we can type the program and save the program with the .sm file, and the assembler is the one which is accepting the your .sm file. It is accepting only the .sm extension files only. Okay, it is accepting only the .sm files. So it is converting the two files into the .lst file and the .obj file. .lst file is listing out your what we say, it is showing all the errors as well as the extra information related to your program, means outputs, all those things. And the .obj file is including only the addresses, that is the relative addresses as well as the what is that opcodes only. Okay, now it is not there in the mnemonic format, but here we are having the mnemonic format. The linker is the one which is linking all the .obj files and creating one executable file, assigning the relative addresses, and the locator is the one which is converting the exe file into the bin file, means I can take this one exe file into the bin file, right? Exe file into the bin file. Yeah, the linker is converting the sorry, the locator is converting the exe file into the .bin file. Okay, so this bin file is mapped into the memory. This bin file is mapped into the memory. Okay, so this is all about our assembler format. Whatever the assembler which we are using to execute the program, the assembler is following all these steps. Okay, so in the exam, if you want, you can draw this diagram, whatever the diagram I just started. You can draw this diagram in the exam and explain 1 or 2 points about each and every block. Then you are going to get the full marks. You are going to get the full marks. So this block diagram is not there in the textbook. It is only I just created this one, so you can make use of this particular block. You can make use of this particular diagram for the explanation in the exam. Okay, now, because we are having the short question on this particular topic. We are having the short question. So the another case is we are having the last point, which is a debugger, right? What exactly the debugger is the question. Assume that this is my program. I'm assuming that my program is a total instruction 1, instruction 2, means total instruction number of instructions which are there. My program is a 100. We may have the 1,000 lines program. We may have the 5 lines program, 10 lines program, 50 lines program, the 1,000 lines program also. So let us suppose if you are having the 5 lines program and you made a mistake, one of the you made one syntax error or some mistakes you made. Okay, now while typing the program, and when you type the program there is a mistake, and when you are trying to execute that program, then obviously the program is not going to be get executed. It is showing some error. So at that time, if it is a 5 lines program or the 10 lines program, 20 lines program, it is very easy for you to pick out the exact location of the error, to point out the exact location of the error. So it is very easy for you. But if at all you are having the 1,000 lines program or a 100 lines program, then picking the exact location of the error is a little bit difficult for the developer. It is a little bit difficult for the developer. So at that time, what the developer will do is they are going to make use of the debugger concept. They are going to make use of the debugger. They are going to make use of the debugger. Okay, so just note on this one. Though they are going to make use of the debugger. What the debugger will do means, let us suppose you are having the 100 lines of program. So for in this case, I am just taking 100 lines of program. There is a mistake. There is an error. Okay, now I would like to check it out. Where means I did all the things, but I am unable to what rectify the exact error location. Then what we can do is I am going to split up my program into the group format. Means I'm going to first, what I'll do is first I'll execute some 5 instructions. I'll execute 5 instructions first. Okay. So I'll execute 5 instructions and check it out. Do we have any error in this particular 5 instructions? If we don't have any error, then I'll ask the microprocessor to execute the next 5 instructions. And I'll ask the microprocessor, if at all no error is there in this particular next 5 instructions, I'll ask the microprocessor to execute the next 5 more instructions. To execute the next 5 more instructions. Here are somewhere you will come across the error, right? Here are somewhere you will come across the error. So means you can easily pick out the location of the error by executing the group of statements at a time. Means 5 instructions for first time, and the next 5 instructions after means second time, third time, fourth time, like that. So here are some way. So 5 instructions. When you are taking one block of 5 instructions, it may give the error. Okay, at that time you can point out the where exactly the error is occurred. Okay, so this split up means grouping a group of instructions, 5 instructions or 10 instructions or 20 instructions, depending on your requirement. If at all it is 100, then if 100 is going to be, means I can take the 10 instructions as a one group. I'll execute the 10 instructions first, 10 instruction first. If there is no error, I'll execute the next 10 instruction. If there is no error, I'll execute the next 10 instruction. If there is an error, then I'm going to pick out the exact location of the error and I'm going to rectify that particular error. So this process is called as a debugging process. This process is called as a debugging process. Now the question comes at how exactly you can ask the microprocessor to halt the execution, to stop the execution after every 5 instructions or 10 instructions. How many instructions you are specifying? That is going to be done with the help of the one thing called as a breakpoint. With the help of the breakpoint, sorry, I'm going to write over here. With the help of the breakpoint, with the help of the breakpoint, I'm going to inform to the microprocessor that I'm grouping the five instructions. It means execute the first 5 instruction and wait for some key has been pressed on the keyboard. If some key has been pressed on the keyboard, then I'm going to make use of another breakpoint. Means I'm going to insert one more breakpoint over here, one more breakpoint over here, and so on, and so on. Okay. So wherever you are executing the breakpoint, the instructions between those breakpoints get executed at a time. If there is no error, then you can continue the next group of instructions. Okay. So by inserting the breakpoint, we are asking the microprocessor to execute the set of instructions and wait for the developer to press something on the keyboard so that you can continue the next block of instructions. So this is a way of debugging. Debugging means the procedure to identify the location of the error by executing the by splitting the entire program into the group of instructions and executing them in sequential order. Executing them in sequential order. So this is what the debugging operation. This is what the debugging operation. Okay. So I hope all of you realize what exactly the MASM is doing. So means any assembler is doing. So inside the assembler we are having the data block. After that we are having the assembler block. After that we are having the linker block. After that we are having the locator block. And we have the extra feature called as a debugging operation. Okay, extra feature called as a debugging operation. Debugging operation is nothing but when we are having the hundreds or thousand lines of program, identifying the location of the error means the program may get executed, but the values are not going to be shown proper way. I would like to identify that location. Then I am going to perform the debugging operation. So if at all you are having the system at your home, if I'm not wrong, it is going to be the function key F7 in your Turbo C compiler. In your Turbo C compiler, the function key is the F7 or the F12. F7 or F12 or F11 is there. I didn't remember the exact function key, but you can try the F7, F11 or the F12, or otherwise in the window itself you can see the debugging option. So by using that particular key, you can ask the C compiler to execute one instruction, to execute one instruction. So instead of executing all the instructions at a time, to execute one instruction. After executing the one instruction, if you are pressing the enter key, then only it will continue the next instruction. If you are pressing the enter key, then only it will continue the next instruction. Like that we are having. Means in the C program, using that particular function key, which is a breakpoint key, we can execute the program in the debugging format to identify the errors. Okay. So this is all about your programming development tools, program development tools, and which are used in the assemblers. Okay. Now when we are writing the program using one of the assembler, obviously that assembler is having certain rules and regulations. Means when you are trying to means when you are taking an admission into one of the institution, Obviously there are certain rules and regulations for that particular institution. Unique rules and regulations are there for every institution. There is a unique rules. Okay, so means rules are going to be changed from one institution to another institutions, as we know. Here also, when you would like to execute the program, using the MASM, which is nothing but the macro assembler. Using the MASM, when you are trying to execute the program, obviously there are certain rules and regulations which are there by the which are followed by the MASM, So those rules or regulations are going to be indicated. Means when you are writing the program, you are having certain rules. So those rules or regulations are going to call as a assembler directives. Means assembler directives are the commands. Assembler directives are the commands or the instructions. I can't call them as an instruction. They are the commands. The commands which are followed by the assembler directives are the commands which are followed by the assembler means we are having the different types of assembler now. So we are having the TASM. For the TASM, we are having the separate commands to execute your program. For the MASM, you are having the separate commands to execute your program. Okay. So for the ASM86 also, we are having the separate commands to execute your program. Executing the program commands are nothing but rules and regulations. In simple short, you can call it as a rules and regulations. Now, whatever the assembler directives which we are going to study over here, whatever the assembler directives which we are going to study over here, those assembler directives are specific to the MASM. These assembler directives are specific to the these assembler directives are specific to the MASM. Wait a minute. These assembler directives are specific to the MASM. Okay, they are specific to the MASM. Okay, so now let us see what exactly the each and every segment usage, directive usage. What exactly the each and every directive usage. Remember, all these segments, or all these what is that directives, that they should be written in the capital letters. As we are writing the mnemonics in the capital letters, mnemonic, whatever the instructions which we are using, and the instructions as well as the register names which we are using in our programs, they should be written in the capital letters, not in the small letters. They're not in the lowercase letters. Remember that one. They should be written in the capital letters when writing the program in the what is that in the exam, and when you are writing the instruction set of the 8086 microprocessor in the exam. Just remember that the instructions should be written in the block letters, which are nothing but the capital letters. Okay, so here whatever the directives, whatever the rules which we are having under the MASM. Okay, under the MASM, I'll ask this control. Wait a minute. So these are the rule. These are the assembler directives which are specific. These are the assembler directives which are specific to the MASM. Okay, let us go for the first set of directives. What exactly the segment and end is? What exactly the segment and end is? See, ma, I would like to write one program. Let us suppose we have seen one program, one simple program, which is nothing but performing the addition of two numbers. I'll write the program and I'll erase that one. So because of that, what you do is try to note down the program. You just note down the program, because soon after I typed up the program and I'm going to erase that program. Okay, better to note down that particular program. So as the rule says that we are supposed to use a, wait a minute, I'm going to take the space over here. So when you have seen writing the program performing the addition between the two numbers, I'm just taking the two numbers. I would like to perform the addition between the two numbers which are there in the AL and BL content. I'm just taking the 06H. Okay, and after that I'm performing the add operation AL comma BL, and I'm terminating my program with INT 03. So this is what our program. So this is the actual program. Uh, to perform the addition between the two numbers. Now, when you want to execute, this particular program, using the MASM, you can't write the program directly like this. The logic is like this only. Logic is taking the two values into the two variables and performing the addition between them. But you can't write that program directly to the MASM like this, because there are certain rules and regulations for each and every assembler. Which assembler we are studying over here? We are studying about the mass. We are studying about the mass. Okay. So macro assembler. We are studying about the macro assembler. Na? So rules are going to be different. Rules are going to be different. Are we clear? So here, how this program is going to be written is a question. Okay. Na? How this program is going to be written means the same operation is going to be done, but when you are writing the program, this program for executing to execute this program using the MASM assembler, then the rules are going to be changing. What are the rules is a question. So here in this program, if you see this one, we are taking the two variables now. Two variables means two values. Okay. So actually, as per our basic analysis, when we have seen the accessing of the memory using the 8086 microprocessor, when we have seen accessing the memory by the 8086 microprocessor is nothing but it is going to be done in the form of the segments format, in the form of the segment. Okay. So as I said, the memory is divided, virtually divided into the segments. So we are having the 16 segments. So out of 16, 4 segments are going to be executed by the microprocessor at a time. First segment is the data segment. Second one is a code segment. Another one is a stack segment. Next one is the extra segment. Okay. Now this assembler, MASM assembler, is expecting that where exactly your data segment is starting, where exactly your code segment is starting, where exactly your code segment is starting. Okay, now where exactly your stack segment is starting, where exactly your extra segment is starting. So in order to specify explicitly that which segment, which statements are comes under the data segment, which statements are comes under the code segment, all those things we are having certain rules and regulations. So here we are having the two variables now. These two variables are nothing but the data elements. Na? These two variables are nothing but data elements. Means we are supposed to declare two variables, not like this, not like this. We are supposed to declare two variables. We are supposed to declare two variables, and those two variables should be there in the data segment, because the data segment is nothing but it is used for holding the data. It is used for holding the data. Whatever the data elements you are having in your program, those should be separated as a separate statements, and those should be saved in the data segment, not in the code segment, not in the code segment. Now the question comes that what is there in the code segment? In the code segment, the operation, actual operation is going to be done in the code segment. Now in order to mention that which set of statements are going to be declared as a data segment, which set of instructions, sorry, which set of instructions are declared as a data segment, which set of instructions are declared as a code segment, that is going to be indicated, that is going to be indicated with the help of the two assembler directives called as a segment and ends, segment and ends. So I hope you noted this particular program. I'm going to make use of the same program, how to write the program or to execute that program using the MASM software. I'm going to modify this one. Okay, actual scenario is addition only, but when you are writing a particular program to a specific assembler, then you are supposed to follow the rules and regulations. You are supposed to follow the rules and regulations. So means you are supposed to also, you are supposed to identify what are the data elements and what are the instructions. Means all these instructions comes under the code segment, and these two values should be declared as a variables. Two values should be declared as a variable. Those should be there in the data segment. Okay. Now the question comes at how to declare the two variables which are there in the data segment. Okay. Now I'm going to make use of the segment and the ENDS. Segment and ENDS is nothing but the end segment. So I'm just erasing my program. I hope you noted this program. Okay. So now here, what I'm going to do means I'm going to make use of the segment, the directive segment. I'm just using the segment. Okay. Okay. So segment is indicating that from there onwards something is going to be defined. Means when you are using the segment now, from here onwards something is going to be defined. What this particular thing, we are going to explicitly mention that one. So here as per our program, we are supposed to declare the two variables. Okay, one variable should contain the 03, another variable should contain the 06. Okay, so under this I am going to declare the variable. Okay, I am assuming that my variable name is a value 1. My variable name is a name of my variable is a value 1. Now what kind of values we have taken into the L and BL? 8-bit number. So for that I'm just using DB. I'm just using db. Okay, db is nothing but defined byte. Value 1 is nothing but it is a variable name. Otherwise, if you want, uh, yeah, it is a variable name. I'll take the different color code for your convenience. Okay, I'm just defining the db. db means I'm saying to the microprocessor that value 1 is a 8-bit data type. db is nothing but the defined byte. db is nothing but the defined byte. We'll see that one also. db is nothing but the defined byte. Now what we have seen, we are assumed that this AL is containing the 03 na. I'm going to declare the I declare the value 1 na. So I'm going to make use of the, sorry, so I'm declaring one variable value 1 whose type is a 8-bit number. It is a 8-bit variable, and I'm assigning the value 03H. I'm assigning the value 03H. And I'm trying to declare one more variable. Two variables we are having now. So I'm declaring that one more variable, which is a value 2, which is a value 2, value 2. Now it is also what, 06 now, which is also the 8-bit number, right? Which is also the 8-bit number. Because of that, I'm just using the, again, defined byte only. I'm just using the db. I'm just using the db, and whose value is what? Whose value is going to be the 06. Whose value is going to be, no, whose value is going to be the 06, whose value is going to be the 06. Now, so this is a one set of statements. Means I declared the two variables. In our program, we require the two variables, and one variable is taking the 03, another variable is taking the 06H. Okay. So now the only two elements are there now as a data elements. Now I'm going to terminate this group. Means I'm going to terminate this group with ENDS. I'm going to terminate this group with ENDS. ENDS is nothing but end of segment. So now what we are doing over here is, here these are the two variables, these are the two variables, and these two variables are made as a one block. Okay, these two variables are made as a one block. Means whatever the variables which are going to be used in our program, I'm declaring them as a them at one point. Okay, I'm grouping them, I'm grouping those variables as a one segment using the segment and ENDS directives. Segment and ENDS directives are the one, they are used for grouping a set of statements. Those statements may be declaring the variables. Those statements may be the performing the actual operation. Okay. So here, what kind of variable, what kind of statements we have written? We have written the information. We have written the instructions which are declaring the variables. So variables are nothing but the data na. So I'm going to call this particular segment. So remember ma, segment and ENDS is nothing but they are trying to group a group of statements, a set of statements as a one group. They are grouping them, means whatever the instructions which are there between the segment and ENDS, they are combined as a one group. They are going to be used as a one group. Okay, now they are going to be used as a one group. Now this entire thing is one group now. I'm calling this group, I'm calling this group as a, we are supposed to give the valid name. We are supposed to give the valid name. Valid name means we are declaring the variables now. These values should be there in the data segment now. As per our analysis, these set of statements should be there in the data segment. So I'm going to give one valid name saying that my data, saying that my data. So I'm going to take over here. Okay. So my data is a label. Actually, we are giving the segment is starting somewhere na. So segment is started from here na. In order to give the starting address of your starting address, in order to give one reference to your starting address, that is a starting of the segment. I'm just taking one label, it is called as a label, we'll see that one, no problem. So my data is a name assigned to this particular segment. My data is a name assigned to this particular segment means explicitly I'm saying that this is the segment which should be there in the data segment. And I terminated segment na, I terminate the segment using the ends na. So in order to indicate that this is the termination of the my data, again I'm typing the my data. I'm typing the my data means whatever the statements, which are there over here, they are grouped as a one block. They are grouped as a one block with the help of the two directives called as a segment and ENS. For this particular group, I'm giving the name. That name is nothing but the my data. That name is nothing but the my data. If you want, you can give your own name over here. But we are supposed to give the valid name. What kind of segment? What kind of statements these are? These are the declaring the data variables. So that's why I'm giving a valid name called as a my data. Okay, now so my data is indicating that this is the starting point of my data segment and this is the ending point of my data segment. This is the ending point of my data segment. Okay, now so segment and ENS are used for grouping a group of statements as a one block, and this particular block, whatever the statements which are there between these two, this particular block called as a logical segment or logical block. This particular block is called as a logical segment or logical block. And I'm calling this particular block as a my data. I'm calling this particular block as a my data. Okay. Now, how we are going to mention this information to, how we are going to inform this information to the microprocessor using the assembler is, that is a different scenario. Means, in order to say the microprocessor that treat this particular block as a my data, that is going to be done with the help of the another kind of directive. We'll see that one as we move on. Okay, so the next kind of segment directives are the db. So we declare that byte type variables now. We declare the byte type variables. What you do is you just take this entire thing as a one block, just note down on the paper this entire thing as a one logical segment. You just note it down on the paper. Okay, now so the next case is what we have done. We have declared two 8-bit data type variables. Now, how many types of variables which are going to be types, how many data types which are going to be supported by the masm software, masm assembler is a question. So that is nothing but the, we are having the, this particular masm is supporting the three different types of data types. We use it one data type now, which is nothing but the db. Three different types of data types. One is called as a db. db is nothing but defined byte. Defined byte is nothing but define the 8-bit number. Next to data type is a dw. So means, let me take over here. So db, okay now, db again, let me tell you one point. You just note down this as a one block. Okay now, whatever the thing we have seen, you just note down this one as a one block. We are going to see this one. We are going to continue with this block in the upcoming classes. Okay, now upcoming class means when we are executing, we are supposed to write the program which is a performing the addition between the two numbers using the macro assembler. So we are going to use the rules and regulations. I declared the two variables and I'm calling that one as a data segment. We just note down this one as a separate one, and we are seeing the data types which are supported by this one, which are supported by the what is that, macro assembler. So here db is nothing but db is nothing but it is a defined. Remember, these are very important in internal questions. db. Now, defined byte is nothing but it is declaring the 8-bit number. Defined byte means it is used for declaring the 8-bit number. 8-bit number. Okay. Next, dw. So dw means dw, which is nothing but defined word. Remember all these because they are the important questions for your 16-bit internal. I think you are unable to see this, so I'll write the another one. db is nothing but the defined byte, which is declaring the 8-bit variable, which is used for defining the 8-bit number. dw is nothing but the 16-bit define the word, which is used for declaring the 16-bit number, defining the 16-bit number. I'll take the DD over here because here I'm having my photograph. So DD is nothing but the defined double, defined double, and it is used for declaring the 32-bit number, 32-bit number. It is used for declaring the 32-bit number. So that is about the DD. Okay, sorry, DD, which is nothing but the defined double, which is nothing but the defined double. I think we are exceeding the time. Okay, so these are the three different types. These are the three different types which are supported by the. Uh, these are the three different types which are supported by the. These are three different types which are supported by the MASM assembler. Okay, now which is nothing but the macro assembler. Which is nothing but the macro assembler. We will continue in the next class with the explanation of the UQ statement, assume the and rest of the directives which are supported by the which are used by the as macro assembler to execute a particular program. So again, I am repeating that. Just remember the my data segment. My data segment. Okay. I hope you realized the concept. Whatever the directives which we are seeing over here, they are specific to the MASM, means the rules and regulations which are going to be followed by the macro assembler to execute a particular program. Otherwise, you can directly take the AL comma 03H, BL comma 06H and perform the addition, all those things. But when you are following a particular assembler, you should follow the rules of that particular assembler. Okay. So this is all about means we just started the assembler directives of the macro MASM. We'll continue in the next class with the remaining directives. Okay, so you again I'm saying that you better to remember this particular one. You better to remember this particular one. I think we need to add one more instruction over here. We need to add one more instruction to hold the result. To hold the result, we'll continue in the next class with that. Okay, we'll continue in the next class with that. Otherwise, I can't do anything over here. Okay, we'll continue in the next class with that. Okay, so we are supposed to declare one more variable, which is a value 1, value 2 we have taken. You can take the another variable whose name is a result. Okay, and whose name, otherwise take down over here. So it should be there between the above the end ma. I forgot to declare one more variable, so I'm just taking the third variable. We are supposed to hold on the what is that result now. So I'm just taking that one, and the result is also, we are performing the addition between the two 8-bit numbers, then the result is also going to be the 8-bit number. So I'm just declaring the db variable. After that, I'm just initializing one variable. I declared one variable now. I'm initializing that one with the 00h in order to avoid the garbage values. In order to avoid the garbage values, I just declared one variable which is going to be stored the result of these two numbers addition. And when declaring this one, I'm just assigning the 00, initializing that variable. That's it. So after that, you take the ENDS. Note down these three variables as a one block. Okay. We'll continue in the next class. Thank you.